Welcome to the Chapter 9 video where we're going to continue our discussion on energy and energy sources. With this chapter, we're going to focus on non-renewable energy sources. So basically fossil fuels, those types of energy sources and the consequences of those energy sources, or of using those energy sources, I should say. So our outline, we're going to look at major energy sources. We're going to look at resources and reserves. We're going to look at how fossil fuels form, issues related to that. Then we'll kind of finish up with nuclear power and have pretty much a whole section on nuclear power where we talk about how nuclear energy happens, chain reaction, fusion reactors. We'll talk about the fuel cycle, and then we'll look at some issues that are related to the use of nuclear fuels. And so we've briefly kind of mentioned this in some of our energy discussions, but just want to define it for everybody so we have a good idea of what we're referring to whenever we talk about non-renewable energy sources versus renewable energy sources. Okay, so non-renewable energy sources are those that really can't be replaced within our lifetime. Now they can be replaced over millions to thousands of years, but again, that's not fast enough to actually be replenished and to be useful. And so we refer to these energy sources as non-renewable. And these are your fossil fuels, your coal, your oil, and your natural gas. Now, the renewable energy sources can replenish themselves or are actually continuously present and are a feature of the environment. So renewable energy sources are things like solar, geothermal energy, so like heat from the earth, tidal energy, wave energy, using running water. So those sorts of energy sources. If you look at what percentage renewable energy sources provide energy to the world, it's only about 12%. And this primarily comes from firewood because we can regrow trees, and then hydroelectricity because we have dams that use the water to or the movement of the water to run a turbine, which then provides our electricity and our energy. And so those are the differences between the non-renewable energy sources and the renewable energy sources. What we're now going to look at is basically where we kind of find these non-renewable resources. So we'll look at what exactly we mean by a resource and then the reserve. And I should say not where we find it, but kind of how we access and kind of where it's kind of held on the earth, or in what way, basically. So whenever we mean a resource, we're basically referring to a naturally occurring substance. And so it's a substance that the world provides, nature provides, that we can obtain, extract, and use it for some, function or purpose. And so that's what we mean by a resource. Now, a reserve is a deposit that we know of, right? So it's a known deposit that we can extract using the current methods of extraction that we have. It doesn't require some new technology to be developed for us to gain access to it. So we basically can access it right now. The reserves are actually smaller than the resources, and the size of the reserve can change as technology advances, right? So as we figure out new methods to extract, say, other resources, our reserves get larger and larger because we can access more and more. And so what we have here is this kind of figure that shows what the reserves are over the resources. So this whole box is known as the resources. So these are the resources that are available. Now out of the entire area of resources, you have kind of different scales of those resources. Not scales, but opportunities, I guess. And so you have your economic scale, so your least economic versus your highly profitable. The ones that are least economic are the resources that you've identified, but we don't really have the technology to extract. So it's not part of the reserves. The most profitable are the ones that we have identified and have the technology to extract. And that's what we refer to as the reserves, right? So that's this upper right-hand quadrant. Now, there are also the resources that we haven't discovered, but we think they exist, right? So this would be like, how we estimate there's X amount of barrels of oil in a country. So we think based off of known geology and the history of the continent that oil should be, in these locations and probably about this much. And so you can do the same thing with other reserves. And so your least known resources are the ones that you haven't discovered, but we believe they should be there. And then the best knowns are the ones that we have discovered, right? And so your resources can be separated into identified deposits and then the ones that are currently not economic because we can't get them out, or the ones that are identified and economical to extract. That is the reserves. So you've identified those deposits, we have the technology, we have the funding, and it's profitable to extract and use. So again, resources, the pool of resources is always larger than the reserves. And the reserves is what we actually have access to. Now, if we look at how our resources form, we're going to look at kinds of the formation of the different fossil fuels. So first, we're going to start with coal. So several hundreds of millions of years ago, you'll get organic material to accumulate. So for example, plant material will collect underwater. And as it begins to collect underwater, it will start to decay. Decomposition will start happening. And then you'll get this organic material layer on the surface of the bottom of the lake or river or wherever it's forming. Now, whenever you have geological changes or sedimentation, you get those deposits to be covered. And whenever they're covered, pressure gets applied. And then as you get more pressure, it starts to heat. And then it will transform from organic matter into coal, which is what we will then dig up. So for example, you have peat, right, which is organic matter with water that's been accumulating at the bottom of, say, an aquatic environment like a swamp or a lake. And then you get more sedimentation, so increased burial. That leads to more pressure, more heat, and over time, you'll get this change from peat to specific coal types. And we'll talk about these specific coal types here in a little bit. And depending on the type of coal determines the percent of carbon that is in that type of coal. So for example, the anthracite has the most fixed carbon percentage with very little moisture and very little volatile compounds. But now your subbituminous, the subbituminous coal has a lower fixed carbon, more volatile compounds, and then more water in that in that component versus the anthracite. So this is kind of the quote unquote purest coal you can get. And then the subbituminous coal is kind of the least amount of fixed percent carbon. The oil and natural gas will generally originate from microscopic marine organisms, like we mentioned in the last chapter, that accumulate on the ocean floor, and then they become covered by those sediments. You get heat and pressure to convert that biomass into oil and natural gases. And the sediments that they get buried in they start out kind of as this muddy rock layer, but then they eventually will deform into a shell, and then that shell will have pores that will have oil dispersed throughout those pores, and then natural gas tends to form on top of the oil because it's less dense, so it goes above the oil layer. But there's generally a rock that serves as a cap. There's like a rock layer that serves as a cap that prevents the natural gas from seeping out of or seeping through the sediments. And we'll kind of show a picture of that in a couple of slides, I believe. But this figure here is showing just the change of oil reserves. So how much oil we have found. So remember, reserves is what's known and what we can extract. And so in the 80s, we have about 700 billion barrels of oil. And then as of about 8 years ago, we've got about 1,700 billion barrels of oil that are known reserves. Here's a figure that I was talking about where you have the oil layer forming and then the natural gas forming on top of that oil layer. And that gas is prevented from kind of leaving because of this cap rock. Right, so that impermeable cap rock prevents all of this material below from leaving above it. And so what they have to do when they're drilling is they drill down through that cap rock, through the natural gas, and they get that oil. But now as they're pulling up, that natural gas will come out, and then they'll either store the natural gas or burn it off, depending on what their goal is for that oil well. And so as we've shown, there's just been this upward slope in oil reserves since the 80s. And then that just increase has just happened, not because more oil is being made, but it's basically because more oil is being discovered. And so remember, the reserves are what's known and what we can access. And as we've talked about before, there are some issues related to the use of fossil fuels. We primarily use fossil fuels for the world's energy. It's about 80% of the world's energy. Coal is by far the most abundant fossil fuel, and it's pretty much used for generating electricity. There's 4 categories of coal. We just mentioned these earlier. So you have lignite, subbituminous, you have bituminous coal, and then anthracite coal. The lignite, so if we follow this figure here in terms of moisture content, right? So from lignite to anthracite, right? So after the peak, basically, the lignite has really high moisture, low energy in terms of that fixed carbon, and is the least desirable form. And then as you go from the subbituminous, which is lower moisture, higher carbon, subbituminous is used for things like power plants, to bituminous and an anthracite, you get more and more carbon content. And so, for example, the anthracite is relatively rare, really high fixed carbon content, and is used for heating buildings and other specialty uses. Now, the bituminous is the second highest carbon content, generally used in things like steel making, and and it has a lower moisture content as well, which is again really good for producing a lot of energy. Now, the way we get at these coal deposits is through a couple of different extraction methods. One is known as surface mining or strip mining. The other is known as underground mining. So strip mining is when you remove material that's on top of a vein. And this is super efficient, but it's really destructive as well. And so you may have heard of mountaintop mining. This is kind of the same thing. So let's say you have a mountain, and there's like a big coal deposit right here. And so what they would do is they would remove the top of this mountain and then access the coal that way. Okay, and so that's surface mining. So it's basically your strip mining, mountaintop removal, etc. Underground mining minimizes surface disturbance, but it's much more costly and it's also much more dangerous because of instead of accessing it from the surface, you're drilling a shaft to go into that coal deposit. You have to worry about shafts collapsing. You have to worry about all the coal dust that builds up in those shafts, so there's not a lot of ventilation. So miners can get black lung disease. So it's a really bad respiratory condition. And it also costs much more to dig those shafts and to pay workers to go into those shafts and also reinforce them. Now, coal is really bulky. And so after you dig it up, regardless of the method, you got to have a good way to transport it. And so again, you're going to get dust pollution, whether you're doing, strip mining or surface mining. And so all of that material is being released into the atmosphere. Sulfur that we use or from burning coal, right? It releases the carbon and it also releases sulfur. And so we can get what's known as acid mine drainage and acid deposition from that sulfur that's released. Mercury is also released when burned. Mercury can be toxic to organisms in high amounts or even relatively low amounts. And then we get more CO2 in the atmosphere from the burning of coal. So here's an image of different methods that we can use to get at the coal deposits. So here you have original land surface, which is this dotted line. And you can see they've kind of removed the top of the mountain and accessing coal deposits that way. You can dozer a contour bench to get at those coal deposits. Here you have your strip mining, where you can have it like on the surface where you don't need an elevator, or you can go deeper where you do need an elevator to get down into the shafts to access, the coal seam that exists here. You will have waste from this. So all of the material you're removing to get to the coal leads to rock spoils, waste. And so you'll have, a pile of rock spoils. You'll have, construction debris. Not only the materials that you use to that comes from mining the coal, but also energy used for the machines, the oil, the gas. You have spills from that, and you have to make sure you're not polluting from the machines and all of those things. So it's really big effort to get at the coal, regardless of what methods you use. Some issues with surface mining is that you really destroy the upper environmental areas, but we can reclaim and kind of restore those habitats, like we see here in the right image. So this reclaimed strip mine. Some other issues with mining is, say, the mining shafts leave these open areas underground, and these can collapse, and as they collapse, the material all goes down, right? So it all goes down. And if any of you have ever played Minecraft, or your kids have played Minecraft, and you've seen them kind of digging gravel or dirt, not dirt, but the gravel in Minecraft, you'll notice that whenever they dig a place out, it will fall down and replace itself. That material is coming from somewhere. And then if you go on the surface in the game, you'll see holes that has left if it goes all the way to the surface. And the same thing can happen in real life. So that's modeled after real life physics. So this is an image showing subsidence where underground mines have collapsed, and that material has went and filled in these underground mines and has left holes, basically pits in the surface of the landscape. We also mentioned acid mine drainage, and so that occurs when you have oxygen, water, and bacteria that causes the sulfur in the coal to form sulfuric acid, and that acid can be harmful to the environment. If it's up in the atmosphere, it can lead to acid rain, which can kill trees. It changes the pH in the soil, changes the pH in the environment, which could be detrimental to other organisms. Now, oil is a much more concentrated energy source than coal. It burns cleaner and can be easily transported. Can be transported much more easily than coal. You can run it through pipes. You don't have to have machines or trucks to haul the oil, but it's much more difficult to find, and it it does cause less environmental damage than coal mining, but you still get pretty big disasters from transporting oil, and we'll talk about those in a little bit. Now, once a source of oil has been located, it then needs to be extracted and transported to the surface. So remember, you have to dig down to access those oil deposits. So there are a couple of different recovery methods. There are primary, secondary, tertiary recovery methods. So the primary recovery method is where if you have water or gas pressure, and it's large enough that the oil is actually forced to the surface when you drill a well. So say you have surface, you drill down to an oil deposit, right? And when you get to that oil deposit, there is enough pressure from water or gases down underneath that deposit that forces that oil up through the surface, and it basically just comes out on its own. However, if that pressure is low, then the oil has to be pumped to the surface. And depending on how viscous that oil is and the characteristics of the underlying rocks, so the geological characteristics, it could be anywhere from 5 to 30% of the oil from the deposit is extracted based off of these primary recovery methods. Now, viscosity is basically referring to how thick it is. So you can look at the viscosity of solutions or liquids. Water is not viscous. It can kind of flow freely, flows relatively quickly, and is not really thick. Molasses syrup is really viscous, especially when it's cold. It just flows really slow. It's hard to move. If you've ever tried to, get syrup or molasses through a straw, or it takes a lot of force. And so the same thing can happen with oil. The more viscous it is, the more difficult and the more energy it takes to extract that oil type. And so the more viscous oils are worth less than the less viscous oils. Now, from the primary recovery methods, there are the secondary and the tertiary. So secondary recovery is where you have water or gas that's pumped into the well, and it makes the oil come out of the pores in the rock. This allows up to 40% of the oil deposit to be extracted, because if the oil's in the rock, and the rock is made up of sediments and particles, right? So all these are like little sediment dirt particles that we're zoomed into, like if we were looking at it under a microscope. And then within all of these particles, you have oil just kind of in between these particles. Okay. And what you can do is you can pump water into these particles to push that oil out. And so that's what the secondary recovery is. So you can pump water or gas to drive the oil out of the pores, and then you can get it up through your recovery pipe. The tertiary recovery is where you pump steam into a well. And like I mentioned with the syrup, if it's very viscous when it's cold, but it's less viscous when it's hot. So you can pump steam into a well to lower the viscosity of the oil, to basically heat it up a little bit. You can also pump gas or chemicals into the well, and get some more viscous material out that way. Like I mentioned, these are expensive methods to get oil out, and they use these with high oil prices. And so the more viscous oils, right, I said, are not worth as much, and they're higher cost to extract, because they are so viscous and harder to get out of the surface. Now, once the oil is removed from the ground, it's not in a form that's suitable for use. It has to go through a refining process, and you can get a lot of different products from a single barrel of crude oil. You can get different petroleum product, gas, etc., from a barrel of oil through that refining process. And now, like I mentioned, oil can be harmful to the environment. It's not as, it doesn't cause as big of effects in terms of how it's extracted versus coal. But there are large disasters that happen with oil spills. So you can have oil tankers to wreck and to spill oil, millions of gallons into the ocean. That causes really big problems. Pipelines can burst. And so accidental spills are only 10% of the oil pollution, though. 90% comes from other mechanisms that happen with the transportation of oil. And the effects of oil, now we know they're bad, we know they harm the environment, but a lot of the kind of specific effects researchers are still looking at to try to understand exactly what happens with those types of pollutions. So here's an offshore drilling rig where they're drilling down, accessing a deposit that's underneath the surface of the ocean. And this is showing secondary recovery from a terrestrial well, where they have water injection wells that push water down into the rocks, and that forces the oil out of those permeable spaces into the pipe to be brought up through that pump and pumping unit. If you're from Kern County or Southern California, you've probably seen a lot of these horsehead pumping units. Kern County is one of the bigger oil producers in the state of California. And so if you're from that area, you're probably familiar with these types of kind of oil rigs. Now, like we mentioned, transportation of oil, boats or pipelines will move oil across the globe. When we look at environmental issues of oil, right, only 10% of human-caused oil pollution comes from tankers. Oil pollution generally comes from ocean oil drilling and kind of the side effects of that. Natural seeps, so oil just kind of seeping into the environment naturally, and then the consumption. So a lot of the oil pollution comes from leaking out of cars, out of boats into the environment, not getting rid of oil waste appropriately, people changing their oil and then just kind of throwing it in their backyard or not disposing of it properly. And so a large portion, 38% of oil pollution comes from how we consume and use oil on a regular basis. Okay, so next, looking at natural gas. So the drilling operations that obtain natural gas are really similar to oil. It's really hard to transport natural gas, and so a lot of oil rigs just burn it off as it's leaking out or coming out of the oil well. it's actually the least environmentally damaging fossil fuel. There's really no air pollution, minimal air pollution with the burning of natural gas. But again, transportation's hard, and so we're still trying to get new transportation methods to help kind of make use of that natural gas. The kind of big thing is the safety of the loading facilities of these natural gas deposits. And so they're generally located offshore, and is so just to kind of increase safety and reduce risk, that sort of thing. Okay, and so that's it for kind of the big three, right? So coal, oil, and natural gas. What we're going to look at now and talk about for the rest of the chapter is nuclear power. Okay, so nuclear power, it doesn't come from a fossil fuel. It actually comes from atoms, so radioactive isotopes, and is non-renewable. So you mine your uranium, and uranium takes a while to regenerate, right, from geological processes. But we're going to kind of talk about it in its own little place. And so as of July 2017, there were approximately 450 nuclear power reactors in operation, 59 under construction, and that's over just 14 countries. There are 160 being planned. Most of those are in the Eastern Hemisphere, so Asian countries like China, India, Japan, South Korea. And if we just look at a table of kind of where reactors are operating, the world has a total of about 432. United States has the most at about 100. And you can kind of look at the rest of the world in comparison. We can also look at reactors under construction versus reactors planned. And again, you can kind of see that China is constructing or planning more, whereas the United States is kind of leading away from that. And most of the reactors in the United States are out east, and very few out west. And so now if we look at how nuclear energy is accessed, and so I said it's from unstable radioactive atoms, so radioactive isotopes. And what happens with these radioactive isotopes is that there are large particles that are released through this disintegration of these atoms. So the neutrons, the subatomic particles, the electrons, the protons are released during that breakdown. And the amount of time that it takes for that radioactive material to spontaneously decompose and break down is referred to as its radioactive half-life. So you've probably heard of half-life before. And that's referring to the amount of time it takes for the radioactive material to lose half of its substance. And so if it starts out as at 100%, how long does it take to get to 50%? Or if it's at 50%, how long does it take to get to 25? Or if it's at 25, how long does it take to get to 12.5? So on and so forth. Okay. And now once a radioactive isotope undergoes its half-life, it's actually being converted into a different isotope. And so if we look at radioactive isotopes, the different types that we have, uranium is the fuel for nuclear power plants typically. And its half-life is 700 million years. So if uranium is going to go from 100% to 50%, it's going to take 700 million years. And then to go to 25% is another 700 million years. So it's 700 to get to 50, 700 to get to 25. And so that's 1,400 million years, or 1.4 billion years to get to 25% of material from uranium. Different radioactive isotopes have different half-lives. Uranium, really slow. Thing like carbon-14 is relatively fast compared to uranium, super fast, right? And then iridium is like extremely fast. Carbon-14 is about 5,000 years, and we can use that information to establish the age of a fossil. So if we look at a fossil and we know, oh, it's got 25% carbon-14, we know that it's underwent 2 half-lives. So it goes from 100 to 50, that's 1, 50 to 25 is 2. And if we know that it's 5.7 thousand years, then that means that it is 11.4 thousand years old, right? Because 25% of that material is left. And so that's how we calculate kind of age of fossils in a general sense. And so for radioactive isotopes and nuclear power plants, we use those uridium atoms. And so here's just some other ones: radon, iodine, phosphorus, etc. Now, the nuclear breakdown of those atoms releases the particles and the energy, and that energy is what we refer to as the radiation. Okay, so if you're exposed to radiation, you're exposed to energy that's coming from the breakdown of those atoms. Now, there's different types of radiation. You can have alpha radiation, beta radiation, and gamma radiation. Okay, alpha radiation is from moving particles that are composed of 2 neutrons and 2 protons, and can generally be stopped by the skin layer. Beta radiation is radiation from the electrons, and this generally can be stopped by clear clothing, by glass, by aluminum layers, etc. Gamma radiation is electromagnetic radiation, and it can pass through your bodies. It can go through, a few inch or so of lead. It can go through a meter of concrete. And so you really need a dense material to prevent any exposure from gamma radiation. And now when we are harnessing the nuclear radiation, the energy. All right, sorry about that. My son decided to come visit for a few minutes. So with the radiation, we can harness that radiation, that kind of release of the energy from the breakdown of the atom through the nuclear process. And so we can initiate the nuclear chain reaction through what's known as nuclear fission. And this occurs whenever you take neutrons, you basically slam those neutrons into the nuclei of other atoms and cause those atoms to split. And the splitting of a nuclei releases other neutrons that causes them to collide with more nuclei, and it releases even more neutrons. So you basically have a chain reaction, right? So this figure just kind of shows that, where you have a neutron slammed into the nucleus, it splits, causes more neutrons to be released. They hit more nuclei, and it causes more splits to happen and more energy particles to be released and energy to be released. And then that just happens until all of the nuclei have been split. And so it causes that chain reaction to happen. Now, only certain kinds of atoms are suitable for this chain reaction. We've already mentioned uranium. Plutonium is another one. And there also has to be a specific amount of nuclear fuel for that chain reaction to occur. And this is known as critical mass. So if you're below that threshold, then that chain reaction can't occur. You have to be at the critical mass in order for the chain reaction to happen. And it's because you just need the density of atoms for that chain reaction to basically kind of pop off. Now, the nuclear reactor is basically the machine, the device that controls and moderates that fission chain reaction that we just learned about. So when you have, say, a uranium atom that is struck by a neutron, right, it splits in those smaller particles. Strike more, chain reaction continues until the fuel is spent. Or you basically prevent neutrons from hitting other nuclei, right? So it's either spent or you have a way to stop it. Now we can take and, here's my pointer, make control rods of a material that's not able to undergo fission, like boron or graphite, and they can be lowered into the reactor. And this is how we can absorb some of those neutrons to control the rate of fission. So if those control rods are not inserted, then all of the neutrons are kind of flinging around, hitting, other atoms. But if you have control rods in the reactor, they are absorbing some of those neutrons. And so the more control rods you have, the slower the fission rate. The less control rods you have, the faster the fission rate. And so we have what's known as a moderator. So a substance that's absorbing energy. And so again, this slows the neutrons, allowing them to split the nuclei much more effectively. And so again, we're using things like water and graphite as these moderators. And then with the release of that energy, remember, whenever you convert energy into another form, you're always releasing heat. And so you can imagine when you're splitting these atoms, a lot of energy is released and a lot of heat is released. Now, coolant, again, usually water, is absorbing a lot of the heat that's released and manages the heat that's released in conjunction with the release of that energy. So a nuclear reactor basically serves as a fossil fuel boiler, right? So it produces heat, converts the water to steam, which turns a turbine and generates electricity. Pretty much the same thing that coal does. You burn coal, it produces heat, converts water to steam, turns a turbine, generates electricity. Here, you're just using a different source for the heat. Burning coal is the heat for a coal plant. Splitting atoms produces the heat in nuclear power plants. The three common types of reactors for nuclear plants are pressurized water, boiling water, and heavy water. There are things called gas-cooled reactors, not real popular, and there's actually no new plants as of the time of this printing. I should probably look this up and update it. There are no new plants of this type being constructed. And so we're going to kind of look at the different types of reactors. For example, pressurized water, right, is where you have that neutron hitting the uranium, releasing electrons, and converting that into eventually a different atom or a different element. Okay. There are also things known as breeder reactors. So breeder reactors will produce nuclear fuel while they're also producing electricity. So the use of liquid sodium, right, so Na, will move heat away from the reactor core. And so what happens basically is you have a fast-moving neutron, hits a uranium, and produces plutonium. This plutonium is a fissionable fuel, so it can be broken down through nuclear fission. And so basically what you have is you have the heat released by the uranium that produces the plutonium, that then can be used as another fuel source. And then that plutonium can be used in, say, nuclear weapons. And so, not a lot of people want nuclear weapons to be made. And so the topic and the politics behind breeder reactors is pretty sensitive because of that aspect. All right, so next we're going to look at kind of how nuclear fuel is mined and developed. So the nuclear fuel cycle basically starts with the mining of low-grade uranium. And this is from, various resources, various deposits. That low-grade uranium ore is then crushed and milled and treated to concentrate the uranium. So basically you're trying to get the uranium out of the ore because that ore is not pure, right? There's other materials in that ore. The milling of that uranium basically produces, powder known as a yellow cake. And depending on the quality of the ore, you can get anywhere from 70 to 90% of uranium oxide. Now, naturally occurring uranium has about 99.3% non-fissionable uranium-238 and only a small percentage of fissionable uranium-235. So what that means is that the uranium has to be enriched to be concentrated enough for most reactors. So you need to be around 3% of 235 in order for that to work in a reactor. So what they do is they have centrifuges to separate the isotopes. And what happens with a centrifuge is you'll spin the material at a very high RPM, so a lot of rotations per minute. We're talking about like 7, 8, 10,000 rotations per minute. Now, if you remember isotopes, the number of neutrons differ. So that means the mass differs. So uranium-238 is heavier than uranium-235. And so you can centrifuge that powder and the material will separate based off of the mass. And so then you can fabricate the powder into pellets, and those pellets are a specific atom, a specific isotope, because they were separated based off of their mass. And then what they'll do is they'll seal those pellets into metal rods, which is what you may have heard as fuel rods. And then those fuel rods are lowered into the reactor to undergo that fission process. Now, as fission happens, the uranium-235 concentration will go down, obviously because you're splitting those atoms, causing particles to be released, and then those atoms will be converted into a new atom or a new element. So after about 3 years, the fuel rods don't contain enough radioactive material to keep that chain reaction going. So remember that critical mass point. So once that fuel rod gets below that critical mass point, they're then known as spent fuel rods, and then they're just discarded and replaced by new ones. However, the spent fuel rods are still pretty radioactive because they still contain about 1% of 235 and 1% of plutonium. So that means the spent fuel rods need to be discarded in a safe way. And so they have to be managed to prevent environmental damage and to prevent health risk to humans and other life. The rods can be reprocessed, so you can actually separate the uranium from the plutonium and use that to manufacture new fuel rods. But less than half of the world's fuel rods are reprocessed. So this is not a common process to go through. The rods generally will go under long-term storage. countries like India, Japan, Russia, France, and the UK are actually operating reprocessing plants. Maybe I can talk soon. Reprocessing plants as an alternative to storing rods. So basically reprocess so you don't have to store these rods and worrying about waste seeping out or radioactive material getting out into the environment. So basically what happens in the nuclear fuel cycle is summarized in this figure. So you mine and mill the uranium, you convert it into the enrichment. You go through that conversion to enrich it. And then once it's enriched, it then can be fabricated, right, into fuel rods. You then use those fuel rods, and then the spent fuel rods can either be reprocessed and turned back into uranium, or it will go into waste storage, long-term storage. Now, every step in this process generates waste. It's not just when it's at the reactor that generates the waste in the fuel rods. And so each step actually involves getting rid of radioactive materials and transporting that waste. And so there's a possibility at every step that radioactive material can be released into the environment and that humans can come into contact with it. So most of the concerns about nuclear radiation and the use of nuclear power plants is associated with the danger of coming into contact with that radiation. So there's what's known as an absorbed dose, which is the amount of energy absorbed by matter, and it's measured in grays or rads. You probably are more familiar with the term rads. Now, especially if you've played maybe games like Fallout, that sort of thing. The damage that you get from alpha particles, right, so remember those alpha particles that we talked about, is 20 times greater than that caused by beta particles and gamma rays, okay? The dose equivalent is the absorbed dose determined by a quality factor, and that quality factor will be established depending on like the type of radiation absorbed. Okay, so now after talking about how you can be exposed to radiation, let's kind of look at the effects of radiation. So when those types of radiation, regardless of alpha, beta, or gamma particles, right, interacting with the atoms, say like in our body, they form the ionizing radiation. And this ionizing radiation, it affects our DNA and can actually lead to mutations in our DNA sequences. Now, mutations, right, so let's say if you're familiar with DNA, right, it's this double strand, right, that's made up of base pairs, right? So like A, T, G, C, A, A, right? So adenine, thymine, guanine, cytosine. And then they are paired together where G will always pair with C and A will always pair with T, okay? Now, downstream through some processes, the DNA is turned into RNA, which is then turned into a protein. Right? And the protein is what allows our body to do cellular processes, and it kind of governs what our cells are going to do. Now, when the sequence is correct, you get the correct protein. But now let's say you have radiation come in and it causes a mutation, and maybe it changes this G. And so now all of a sudden it's an A. And when that is replicated, this opposite strand will also be wrong. So it would be TAT instead of C. Now this is going to code for maybe a different amino acid compared to what the original one was, and so that will change the protein downstream. Now when you start changing the proteins, you can alter the function of those proteins, and then the functions can not cause the cells to function properly. It can cause the cells to divide and grow faster than normal, which is what leads to potential cancers. And so that's kind of how the mutations affect our bodies downstream. Large doses of radiation, though, could be lethal, could be fatal. You can get radiation sickness. But knowing how radiation affects bodies in smaller doses is kind of the difficult part. The more radiation you receive, the more likely you're going to have some sort of negative consequences, biological consequences, right? So it's important to reduce this. If you are coming in contact with radiation, that you reduce the amount of time, you try to be as far away, and you try to shield yourself from those radiation particles. Some of the more common shielding mechanisms are lead, concrete, and water. So for example, the shields that you use when you get x-rays, I believe, have lead inside of those shields. Those of you who are in health fields or associated with health fields will probably know more, but I'm pretty sure that they're lead shields that they like put over your body and your organs. So like when you're getting an x-ray or some other image, to prevent the radiation from going into those parts of your body. So there's quite a bit of protective equipment that you could wear. So like these suits, you can do detectors, which is what's shown here, where it's detecting how much radiation you may have absorbed. And depending on the source of radiation really determines how much radiation you would have been exposed to. So for example, a nuclear bomb or exposure in a nuclear facility could be about 100,000 per incident. That's enough to kill you right away. Nuclear accident or exposure to x-rays, depending on the severity, could be really bad. So comas, death in a couple of weeks. Eventually, maybe if you have good medical care, you can survive. And then the lower the doses affect, long-term stability. So like mutations leading to different cancers, etc. And then really small is where it gets difficult to determine what those effects are going to be. Now, for reactor safety, so for example, one of the more famous ones is the 3 Mile Island nuclear plant in Pennsylvania that had a partial core meltdown in '79. So basically what happened is a pump and valve malfunction. You had operator with some sort of error that added to that problem, and the containment structure prevented the release of radioactive materials, but the steam was vented into the atmosphere. And now that reactor was basically broken, and it was defueled, and it cost about $1 billion to actually get rid of that. The radioactive steam went into the atmosphere, and it could have immediate effects or long-term effects in the surrounding environment and the populations living near that island. And so that steam could expose organisms and people to radioactive material. Now that fuel was placed in storage until its companion reactor reaches the end of its useful life, and then they'll dispose of it as necessary. So here's an image of 3 Mile Island. Another really famous, probably the most famous, is Chernobyl, which is in Ukraine. It's the world's largest nuclear accident, which happened in '86. And so basically there were safety rules that were violated. Automatic warning systems weren't heated appropriately, and it caused the emergency core cooling system to not work appropriately. And you get this really quick energy level increase. So in about 5 seconds, you get 2,000 times the energy that you were supposed to have. the cooling water converted to steam because of that and blew the concrete roof off of the reactor, a 1,100-ton roof. The reactor core caught fire and it basically burned for about 10 days. Now, associated with this accident, there were 37 deaths due to the accident, 500 people hospitalized, cities evacuated. 237 of those people had acute radiation sickness. 25,000 people almost got really high doses of radiation, which means that they could have long-term effects. Children exposed are showing increase of thyroid cancer because of the radioactive iodine that was released, which again is just, really bad long-term effects that weren't really necessary and shouldn't have been exposed to the population. So here's, where the plant blew and released the material into the atmosphere. Now, Fukushima is a more recent nuclear power plant that was damaged. So this was damaged when the tsunami hit in 2011. So the heat exchangers were damaged because of the natural disasters. And so the power was cut off to the site. And the diesel generators were flooded and stopped operating. So basically, all the safety stuff just was removed because of the tsunami and the damage from the earthquake and the water. So you had explosions, fires, and leaks into the cooling system, which caused radiation to go into the atmosphere and the seawater. Now, there are events of terrorism that could lead to kind of nuclear fallout, where you have, nuclear bombs or the release of nuclear material. And so after September 11th, there was a big kind of concern for nuclear plants being the target of such attacks. And so, they kind of looked into and implemented safety measures to kind of help prevent any of these types of events from happening. Now, when we look at power plants, they obviously don't have an infinite future. The life expectancy of most power plants are 30 to 40 years. Unlike other power plants, though, nuclear plants are decommissioned. They don't demolish them like, say, a coal plant. Decommissioning comes in a two-step process. So one, you remove and properly dispose of the fuel rods and the water that was in the reactor, because that water is going to have radioactive material. And then stage two will be the final disposition of the facility, so the final decommissioning of the facility. There are three options to that second stage. You can decontaminate and dismantle the plant. You can secure it for many years to allow the radioactive materials that have that quick half-life to disintegrate and then dismantle the plant. Or you can entomb the contaminated proportions by covering the reactor with thick reinforced concrete and placing a barrier around the plant. This is the only option really considered for suitable small kind of nuclear research facilities. And so with nuclear power plants, there's a lot of waste that is generated, not only in the fuel waste, but also just in the plant itself whenever it's not being used again. And so you're really kind of taking away from that area. So that area is really not going to be able to be used for anything else once you build a power plant there. So as of today, there are about 160 commercial power plants and about 48 experimental plants that have been shut down and are in decommission stages. The cost for decommissioning a large plant is expensive. It's like 200 to 400 million, about 5% of the cost of generating electricity. And so, it kind of goes to look at what's the pros and cons of these power plants, in terms of the power that they're giving us, cheap, efficient power, or is that good enough versus, kind of the cons, the downsides that can exist from these power plants in terms of accidents, decommissioning, funding to do that, etc. So that's pretty much it for was this chapter 9, about non-renewable resources. So here are the summary pages. Like always, look at them to study. Again, these are not the all the key concepts that you need to focus on, just a good starting point for studying. As always, let me know if you have any questions, if you have any concerns. You can contact me through email or the class discussion board. And I hope you have a good rest of your day, and we will see you in the next chapter.